Dear students, in the last class, I have explained very important concept called electric potential. So, what is the definition of electric potential? Electric potential at a point is defined as work done in moving a unit positive charge from infinity to that point against the electric field. The SI unit is volt, it is a scalar quantity, and work done in moving a charge Q naught from A to B is given by Q naught into A to B. So, B is the final point. So, final potential minus the initial potential, where Q naught is the charge moved, VB is the potential at B, VA is the potential at A, and VB minus VA is the difference in the potential, which we call potential difference. Is there any relation between electric field and electric potential? Yes, and that is what we are going to derive now. The relation between the electric field and the electric potential due to a point charge. So, this question has appeared 6 times in the examination. So, it has appeared this year March 2020, and it has appeared even in the supplementary exam as well. So, what is the relation between electric field and electric potential? It is a 3 marks question. So, very easy and simple. And to understand that, let us consider 2 points. Point A and this is the surface containing the point A having potential V. At a certain distance dl, at a small distance dl, there is another point B, and this is the surface containing point B. Surface containing point B. So, this surface is at a potential V plus dV. So, V is the potential at A and V plus dV is the potential at B. So, that the potential difference between A and B is dV. So, dV is the potential difference between A and B. And let E be the direction of the electric field here. So, which is upward. So, E is the electric field which is in the upward direction. So, we are going to consider a unit positive charge which is plus 1 coulomb and is moved from B to A, from B to A, and in doing so we have done some work dW and we can find that work. So, what is the work done in moving a unit positive charge from B to A? It is given by charge moved, which is 1, into potential difference. It is moved from B to A. So, potential at A, which is V, minus potential at B, which is V plus dV. So, this will be equal to minus dV. So, V will get cancelled, we will get minus dV. Work done is also given by the electric field into the distance through which the charge is moved, which is the dl. So, the work done is also given by the product of the field and the distance through which the charge is moved. So, equating this equation, we will get minus dV is equal to E dl, therefore, E is equal to minus dV by dl. So, this is what the relation between the electric field and the electric potential. This minus dV by dl is called potential gradient, electric potential gradient. So, therefore, electric field is always equal to negative electric potential gradient. Electric field is a vector. So, electric potential gradient is also a vector quantity. Based on this, we can write one of the unit of electric field. One unit is Newton per coulomb. which we already know. The other unit is volt per meter. So, electric field has a two unit, one is Newton per coulomb and the other is volt per meter is the second unit of electric field. So, this is what you have to write for this particular question. So, consider two surfaces at potential V and V plus dV. A charge is moved from B to A and the amount of work done is equal to the charge moved, which is 1, into the potential difference. That will give you minus dV. Then work done is also given by the product of the field and the distance through which the charge is moved, and by equating you will get E is equal to minus dV by dl. What is the electric potential at a point due to a point charge? So, this question has appeared once in the exam. We know electric field at a point due to a point charge. For example, if I take a charge q at a distance r, the electric field is given by 1 by 4 pi epsilon naught q by r square. Similarly, at this point at a distance r from a charge, what is the electric potential? So, that is what we are going to derive now. So, I am going to consider a source charge at point O. So, the charge is q. At a distance r, there is a point P where I want to find the electric potential at a distance r. And how do you find potential at a point? Potential at a point is measured as the work done in moving unit positive charge from infinity to that point against the electric field. So, let me assume somewhere here. So, this is the reference, which is infinity, and I have to measure the work done in moving unit positive charge. So, unit positive charge is moved from infinity to that particular point. To measure the work, I have to find the force, because the work is equal to force into displacement. So, force is variable here because it varies with the distance. So, that is why I consider 2 points, one is A, other is B, at a separated by distance x, not x, dx, and let that point A be at a distance x from the charge, and we have a unit positive charge here at A. So, what is the force experienced by this unit positive charge? It is given by F is equal to 1 by 4 pi epsilon naught q by x square. That is the force experienced by unit positive charge. And how do we get this? By using Coulomb's inverse square law formula. F is equal to 1 by 4 pi epsilon naught, product of the charges, q into 1 by x square. Distance is not r, it is x. Now, this unit positive charge is moved from here, from A to B, through a very small distance. So, what is the small work done? So, work done is equal to minus F into dx. So, minus, because the force on it is in this direction and the displacement is in the opposite direction. So, force and displacement are opposite. So, that is why it is minus F into dx. What is F? Here it is, 1 by 4 pi epsilon naught q by x square into dx. So, this is the small work done in moving unit positive charge from A to B. But we want to find the total work done in measuring, in moving the charge from infinity to point P. So, what is the total work done in moving the unit positive charge from infinity to the point P? And that total work done we calculate by integrating. So, charge is moved from infinity, therefore, the distance x is equal to infinity, that is the lower limit, and then the charge is moved from infinity to the point P. When the charge is shifted to the point P, the value of x becomes equal to r. So, infinity to r, and then add such small work, you will get the total work done in moving unit positive charge from infinity to that particular point. Why are we moving the charge to the point P? Because that is the point where we want to find the electric potential. So, this is equal to infinity to r. The value of dw is nothing but, here it is, minus 1 by 4 pi epsilon naught q by x square into dx. Now, write the constant outside the integration. So, w is equal to minus 1 by 4 pi epsilon naught, and then even q, this is that q, and then integration infinity to r, and what is left within the integration is only 1 by x square into dx. And here we are going to use one integration formula, that is integration of 1 by x square dx is equal to minus 1 by x. 1 by x square dx is equal to minus 1 by x. So, that is minus q by 4 pi epsilon naught minus 1 by x, and then write the limits outside, infinity to r. This minus of minus becomes plus, you will get q by 4 pi epsilon naught into 1 by x, the limits infinity to r. So, time to substitute the limits now, 1 by 4 pi epsilon naught into 1 by r, replace x as r, 1 by r, minus 1 by infinity. Now, that is w. 1 by infinity is 0. So, therefore, w is equal to 1 by 4 pi epsilon naught q by r. But the w itself is equal to V. V means electric potential. So, therefore, V is equal to 1 by 4 pi epsilon naught q by r. So, this is the expression for electric potential at a point due to a point charge. How different this equation is from that of electric field. In electric field formula, we get E is equal to 1 by 4 pi epsilon naught q by r square. But here we get V is equal to 1 by 4 pi epsilon naught q by r. So, this is an important derivation for 5 marks. So, if I consider a point charge q at a distance r, the electric field is given by E is equal to 1 by 4 pi epsilon naught q by r square, and potential at that point is 1 by 4 pi epsilon naught q by r. And if I divide this equation, I will get E by V. If I divide E by V, this will get cancelled, Q will get cancelled, one of the R will remain in the denominator, it will be equal to 1 by R. Therefore, from this we come to a conclusion that E is equal to V by R. So, that is the relation between electric field and the electric potential at a point due to a point charge. E is equal to V by R, E is equal to V by R, or V is equal to ER, V is equal to E into R. So, that is an important relation. Now, due to negative charge, instead of positive charge, if I consider a negative charge, then electric field at that particular point will remain the same magnitude, E is equal to 1 by 4 pi epsilon naught q by r square, and that it is directed towards the charge. But potential is minus 1 by 4 pi epsilon naught q by r. So, that means while calculating the potential, you have to consider the sign of the charge. But while finding the electric field, we do not consider the sign because it is a vector quantity. The direction will give you an idea that this particular charge is a negative. But while finding the potential, signs are very important. If there are many charges, system of charges Q1, Q2, Q3 and Q4 and so on. Then how do you find the net electric field? The net electric field is always given by the vector sum of the electric field due to individual charges, vector sum, because electric field is a vector quantity. Whereas electric potential is given by the algebraic sum of the potential due to each charges, algebraic sum. We have to just add them. So, what is common for all the potential? 1 by epsilon naught into first charge by its distance Q1 by R1 plus Q2 by R2. So, this is R2 plus Q3 by R3 plus Q4 by R4. So, this is how we find the net potential at a point due to a system of charges. When more charges are there, many charges are there, just add the potential due to each charge. And if there is a negative sign, apply the sign here in this particular equation. So, this is an important equation to find the net potential due to system of charges. For single charge, we use the equation V is equal to 1 by 4 pi epsilon naught Q by R. But if there are many, then we add them algebraically. And along with this, the equation which is important is this: W A to B is equal to Q naught into V B minus V A. That is work done in moving. A charge Q naught from A to B is given by Q naught into V B minus V A. So, hope you have understood all this mathematical format related to electric potential and electric field. They are important, and in the next class I am going to solve numericals based on these topic. Thank you.